Hi, my name is Ryan Lewis, and I'm a machine learning researcher currently located in Berkeley, California. Today, I'll be discussing my investigation, which uses a deep reinforcement learning model to simulate autonomous vehicles that can operate effectively in traffic alongside human drivers. This is going to be a fairly high-level overview of the project. However, if you have any technical questions, feel free to reach out. I've included my contact information at the end of the video. So I'm going to start with a brief overview on some of the current problems we face with traffic in cities and urban neighborhoods. Next, I'll talk about how we can use reinforcement learning to address this problem, which tools we need for the job, some results and insights from developing this project, how this model can be further developed, and a final overview of how this can be applied in the real world. So why should we care about traffic density? Well, as more cars start using the same routes, we see increased commute times and increasing energy usage in the form of burning fossil fuels and battery discharge for electric vehicles. To address this problem, I wanted to create a baseline model to improve upon. I started by placing 20 drivers, which mimic the behavior of human drivers in the city environment you can see here on the right, and recorded their average speed. After that, I kept adding vehicles to the simulation until the average traffic speed dropped by 50%. Which, as you can see on the chart on the left, occurred when there were 140 cars in the system. Knowing that I wanted to improve upon this model with 140 cars, it was time to start replacing some of those human model drivers with autonomous vehicles. The autonomous vehicle model I implemented takes 6 different values as inputs and then feeds them into a neural network, which determines the rate at which it should accelerate or decelerate. Those 6 values are the speed and position of the autonomous vehicle, as well as the speed and distances of the cars directly in front of and behind it. Several libraries were required to create this model. On the right, you can see OpenAI Gym and Sumo, the simulation for urban mobility, which were used to simulate the environment for the vehicles. And on the left, you can see Ray's Tune and RLlib libraries, along with TensorFlow, which were used to create the autonomous vehicle model. Last but not least, Flow is used to tie these libraries together and deploy the autonomous vehicles in the simulation environment. I started by creating models where 10%, 20%, and 30% of the human drivers were replaced with autonomous vehicles and trained them for 50 episodes. These models were scored using a reward function, which looks at how close all of the vehicles in the system are to the speed limit for the section of road that they're currently traveling on. The reward is accumulated throughout the course of each simulation and reset before starting the next one. This is important to keep in mind for later. Since the model where 10% of the human drivers were replaced with autonomous vehicles seemed to be performing the best, I decided to investigate it further by running 2 additional training sessions. Here you can see the first, second, and third training sessions, which each picked off where the previous one left off. There was a decent improvement from the first training session to the second, but the model score did not improve much in the third training session. This is likely due to the fact that the coefficient which controls the amount of time the autonomous vehicle spends exploring different policies is reset at the beginning of each training session, and the model spends more time trying to decide which strategy is best as opposed to optimizing one. As I mentioned earlier, the reward score is accumulated throughout the course of the simulation. This is important because the simulation will end if any of the vehicles collide, and the reward value will stop increasing. This graph shows the average simulation runtime for each of the 3 training sessions, and you can see that in the third training session, the autonomous vehicles had started learning to mitigate collisions, which would end the simulation early. Here you can see a clip of one of the simulations where the autonomous vehicles are blue and the human drivers are red. And that was fairly brief, so if you didn't catch that, I'll play it one more time. So in conclusion, less is more. And having a smaller percentage of autonomous cars is better for initial training. For simulations with high percentage of autonomous vehicles, it would likely be best to initially train the policy using a system with a lower percentage and then transfer that policy to an environment with a higher percentage of autonomous vehicles. This is because it reduces the complexity of the simulation as the autonomous vehicles are interacting more frequently with the predictable human drivers as opposed to themselves. Currently, I'm using the proximal policy optimization algorithm from RLlib to train the neural network and schedule the simulations to run. This is done synchronously and updates the model after 21 simulations have occurred. This means that there's a brief lull where the model is waiting for the simulations to finish before it updates and starts scheduling new simulations. I believe that using the asynchronous version of PPO, which reduces this lull by performing updates in a more continuous manner, would be better for continued experimentation. I also believe that this model could be highly relevant to applications of federated learning, where autonomous vehicles can learn to adapt to their local environment rather than having one global policy which controls the behavior of all autonomous vehicles in a system. Going forward, I'd like to incorporate Carla into my model in order to produce a 3D representation of each autonomous vehicle's surroundings. This would allow my model to create more nuanced policies like lane keeping and object avoidance by using another neural network to interpret simulated dashcam footage and other sensor data. Thanks for checking out my project. Email and LinkedIn are the best way to get in touch with me. And if you'd like to see the documentation for this project, please check out my GitHub repo, which contains the documentation and resources for this project, along with other projects I've worked on.